Hey guys, hope you're doing well. I've been praying for you. Just know it's a crazy time of life here, but we just gotta keep on trying our best here to hang in there, and God will help us get it all through this all. We're gonna do next lesson here, so let's just jump into it. Section 2.6, graphs of rational functions. So we focused on polynomial functions last few lessons actually. Here we're gonna look at rational functions. Now, what the main difference is rational functions are functions that you can write as fractions, okay? So rational function r of x is equal to f of x over g of x, where f of x and g of x are polynomial functions. So rational function is just comprised of polynomial functions. Now, if g of x doesn't have a variable, then it basically is a polynomial function. But here we're going to have variables in both the numerator on top and the denominator on the bottom. Okay, so let's look at example 1 here. Find the domain of the function f. Use limits to describe the behavior of f at the values of x not in its domain. All right, so here this is a rational function. And remember, you cannot divide by 0. And so if x was equal to -3, it would give you an error. And so that's a domain restriction. All real numbers except for x equals -3 are in its domain. So wherever there are divide by 0 possible errors, provided that factor that creates that is not also in the numerator, then that's going to give you a vertical asymptote. So we have a vertical asymptote at x equals -3. And we could write what this function's doing with limit notation here. So as x approaches -3, and then remember this minus sign here means from the left side, okay, it's equal to -infinity. And likewise here, if we're approaching it from this plus side, which is the right side, approaching -3, it would be equal to infinity, okay? So what does the graph of this function actually look like? Well, remember one of your basic functions is, let me move my little pen tool here, ignore that. One of the basic functions is the reciprocal function, okay, 1 over x. All right, and so these are all the characteristics of 1 over x. You have a horizontal asymptote at y equals 0, so it gets really, really close to y equals 0. You have a vertical asymptote at x equals 0. All right, and then this describes its end behavior, okay, as x goes to infinity and -infinity. This particular graph is called a hyperbola, all right? Now, this particular function here is related to this particular function here, okay? The only difference is the +3, okay? So what you have essentially done is you have changed the input of the function. So instead of it being 1 over x, it's now x plus 3. Okay, now when you change the input of the function, that causes the graph to shift left or right. Okay, because it's +3, you now need a -3 to act the same way as a 1 over x or a 0 would act. So what this graph would look like is this same reciprocal function, only it will be shifted, and here's the vertical asymptote at x equals -3, and then you'd have a horizontal asymptote at as x approaches infinity. So it would look like this essentially. Same shape, just shifted to the left 3. Okay? So just keep that in mind when you see functions, you're relating them to the reciprocal function. All right? So now let's get a little bit more intense here. So now we have any rational function of this form here. Okay, now this is a linear form, okay, ax plus b over cx plus d. All of these types of functions are just transformation of the reciprocal functions, okay? And then it wants us to look at example 2 on page 220, so you could do that in your book, but I'm going to do that here. So if the degree of the numerator is greater or equal to the degree of the denominator, we can use polynomial division to rewrite it, okay? That way we can see the transformations a little bit better. Now that's especially useful if the degrees are the same here. Okay, now let's actually show you what happens on this particular one. Okay, so here you have 3x minus 7 over x minus 2. You have no idea how this relates to the reciprocal function until you do polynomial division, okay? So you're dividing. Remember, always put the numerator inside here, okay? So we're taking x into 3x. X goes into 3x. How many times? All right, so that's 3x divided by x. That's just 3 times. Okay, so, and actually we should, let me undo that here. We should put the 3 above the constant term because it's the constant term, not the x term. Then we would multiply 3 times negative 2. That's negative 6. All right, and 3 times x is 3x. All right, so after you multiply, remember when you're doing long division, you subtract. Now, even though this is a minus sign, because we're subtracting a negative, that becomes actually a plus sign. And so we have negative 7 plus 6, which is equal to negative 1. You notice how I circled my signs here? That just reminds me that I changed my sign. So when I'm doing long division of polynomials, I generally circle the sign so I remember that I changed it. All right, so I have 3. Now remember how you write this. You take your remainder, you make it into a fraction. Okay, so it's 1 over x minus 2. Okay. So now if we're comparing it to the reciprocal function, all right, so we have changed the input, so it's the reciprocal function moved right to, okay, and then there's a negative outside of it, so this is actually going to be a reflection over the x-axis, and the final transformation here is this 3, okay, now the 3 is on the outside, so it's just going to shift it up 3, okay, so this graph here, now that we've changed it and we looked at this polynomial, we can see that it's a horizontal translation, a reflection, and a vertical translation, up 3. All right, so this is what we're comparing it to 1 over x when we're talking about this. Okay, so hopefully that helps you understand how to relate to a base function when in terms of rational functions. Now, not all of them can be related to the reciprocal function 1 over x. All right, we'll look at some more tricky ones next. Okay, so you can find the asymptotes by translating the known asymptotes of the reciprocal functions, which is what we did. You can use graphing and algebra to find them as well as considering the limits here. All right, so y equals b is called a horizontal asymptote if you have one of these two things being true, okay? It doesn't have to be both cases. It's just as x goes to infinity, the function goes to b, okay? Or as it goes to negative or positive, it doesn't matter, okay? Both of them could approach b, but it doesn't have to be both. It could be just one-sided approach b. And here is the definition for a vertical asymptote. The line x equals a is a vertical asymptote if both of these are true, okay? It approaches infinity from the left and also the right, okay? Or negative infinity. So we've seen those before. All right, then it wants us to look at example 3 on page 220. So I want you guys to go ahead and pause the video, check it out. Okay, let's continue here. So when we're considering horizontal asymptotes, remember how we can figure those out. We compare the highest degree in the numerator compared to the highest degree in the denominator. All right, and then there are these different cases. And if the one on the top is higher, there's a horizontal asymptote at y equals 0. If they're equal, then you put the leading coefficient over the other leading coefficient. Okay, and you reduce that to figure out where the horizontal asymptote is. And if the top degree is bigger than the bottom degree, then you find the horizontal asymptote. Actually, there is no horizontal asymptote. I apologize there. You actually get the asymptote by doing long division. And if you get a linear, if you do long division and you get a linear q of x, then guess what? That's called a slant asymptote. So it'll approach a slanted line. All right, we'll talk about that more in a second. But vertical asymptotes, okay, zeros of the denominator, provided that the zeros are not also zeros of the numerator, of equal or greater multiplicity. So anytime you have a factor in the denominator, as long as it has higher multiplicity, which means it doesn't cancel out with the numerator, then that is a zero. No, that's not a zero, that's a vertical asymptote, okay? The x-intercepts are zeros of the top, or zeros of the numerator, okay, which are not also zeros of the denominator, because if they were in both, then remember that is the case where you would have a hole, okay? The y-intercepts, you just plug in 0 to find, and so we're going to do example 5 on page 222 together here, because it's very critical that you guys get this for this lesson. This is what this lesson's all about. Okay. So let's run down through all these different things in example 5. Okay, here's the function. The x-intercepts. To find the x-intercepts, all you got to do is set the top equal to 0. So this one's real easy. X minus 1 set equal to 0. If we solve it, the x-intercept would be x equals 1. Now you might have to factor, okay, in order to find the x-intercepts. If there's a bunch of stuff on the top and it's quadratic, x squared, you probably have to factor. All right. The y-intercepts, we're just going to plug in 0 for these x's. So we would have 0 minus 1 all over 0 squared minus 0 minus 6. So it looks like our y-intercept is at negative 1 over negative 6, which is positive 1, 6. Okay, so that's your y-intercept. Just remember, just plug in 0. Okay, the asymptotes. Now this is where we're going to have to factor the denominator, and we would have to factor the numerator too. See if there are any common factors on the top and the bottom. Okay, so the denominator would factor into x. Okay, remember we want to try to make the middle term. The middle term is minus 6. So use factors of 6 to make the middle term. And the signs have to be opposite to give you this negative 6. So it's going to be more negatives to give you a negative in the middle. So that's minus 3. Sorry, that looks like a backwards Z. And then plus, because we want to have different opposite signs, plus 2. Then remember to check it, make sure that gives you negative 1. And it does. All right. And then the top is x minus 1. Okay, so there are no common factors here in the top and the bottom. So that means there's no holes. Now, once you have the bottom factored, set each factor equal to 0, and then solve to figure out your asymptotes, vertical asymptotes. All right, so here we go. And then so your vertical asymptotes would be x equals 3, x equals negative 2. All right. End behavior, which means horizontal asymptotes. All right, let's compare the degrees. Top degree is 1, bottom degree is 2. So that would mean n is less than m. Testing.